This is a little bit loud, is it? All good? Okay. Yeah, thanks for being here. So many of you, so close. I'm Carsten from the University of Virginia, and I'd like to discuss with you today and inspire you perhaps to join our efforts of analyzing the security of certain hardware tokens and breaking them. Work I've been doing with Starbuck for a couple of years now, who is just ingenious in working with these. Is this breaking? The noise is breaking? It's good? Okay. Starbuck is just ingenious in working with small hardware tokens and getting all the little secrets out of it. And I'm just giving a little structural advice here and there on how to analyze them further. So a quick summary and the last chance to leave. We'll be looking at hardware tokens such as RFID tags and explain how to get the security functionality out of them and then to analyze it and to find weaknesses. To inspire as many of you as possible to join our efforts to also reverse engineer hardware tokens, but I'll also give pointers to us in the room that might be interested in building hardware rather than breaking it, things to avoid and how to make hardware security better. We are interested in this topic because we see a lot of critical infrastructure, more and more critical infrastructure relying on hardware tokens for the security, be it access control into governmental buildings, be it passports, for instance. There's a lot of non-critical infrastructure too that's secured by hardware chips, TV, for instance, or your printers. Make sure you pay a lot for your printer cartridges through verifying that there's a tiny chip in them, and so forth. And we get the impression that in all these applications, including the critical ones, not much thought is given to making them secure enough. And that might be because the domain of hardware is hard to reach or hard to understand, but it's getting easier and easier to understand and hence easier to break, and we provide the breaking and hopefully somebody else will make the design better. By security, obviously, we don't mean a binary property that a system has or doesn't have, but rather an accumulation of properties where the weakest link of the entire system defines the system's security. So even something unbreakable can be circumvented if another component of your system is weak. Applications will be dealing with here as examples include, for instance, an RFID card that opens a door. So this card will know some cryptographic primitive, a cryptographic cipher that's also known at the door, and they'll both share a cryptographic key. And the card, through some protocol, will prove to the door that it knows the key, and then the door will open. Similarly, in satellite TV, for instance, there's a cryptographic cipher and a cryptographic key used to decipher the signal that comes down from the satellite, and hopefully only whoever paid for Premiere can watch it. So all these applications and all the hardware security applications rely on either a cryptographic cipher or a cryptographic key to be secret. So there must be something that only your customers know, that only your employees know, or their respective cards know. And in hardware security, the mistake is often made that both of these are kept secret and that the security is spread across the two. When cryptography, we very much rely on the cryptographic key that it be secret, where the cryptographic cipher should be some published standard, and it ought not to be secret because people like us reverse it from hardware. So that's what we're going to talk about today, breaking cryptographic ciphers by simply finding them. And since any cipher that isn't standardized is usually weak, we then normally break it within a few days. So I'll walk you through the different steps needed, and I'll try to stress how simple each of these steps is and how little tools are needed. If there's any doubt about it, we can discuss it at the end, and I'll make sure everybody leaves the room with the understanding that you too could be reverse engineering tomorrow. And if time permits, we'll look at some of the impact we have had and potential impact, potentially interesting application that one should be looking at next. A microchip, as you'll find it in a smart card, will look something like this. It's an Infineon 66, which you can always tell by these two triangles here in the middle. Most of this chip area is memory and security. So the actual microchip is only this middle part. And it's a somewhat secure microchip because everything that is stored in these memories is encrypted. If you were to just read out the memories, you don't learn anything. But in order for the processor to work on the data that is stored in the memory, it has to be decrypted. So there's a memory encryptor, decryptor unit, and everything that's read in memories first goes through here and is then processed in the processing core. How do we break this? Well, easy. If it's decrypted here before it goes in here, we wiretap little wires in between here. And these are exactly these wires. So we use tiny needles, poke in there, and we see the bits flowing by. Now, the manufacturers of these chips obviously know that we can do that we can understand that chips that they build very structured. To understand themselves, these chips have to be debugged. So not trying to hide anything in silicon, because nothing can really be hidden. Everything is there once they give you the chip. They come up with other security mechanisms, such as meshes. A mesh is simply a long snake of metal going all across the chip, and if the two endpoints of the snake are not connected, the chip won't start decrypting. So if you start scratching this mesh to get to where your needle has to be put down, the chip won't decrypt anymore. Well, what do you do here? You get away with the mesh with hydrofluoric acid, and you put two needles down where the mesh should be connected and connect those two needles. Now, with a certain needle, you poke on the data bus, and again, you read the data. This game has been going on for a couple of years now. FlyLogic has been taking apart every single chip, I think, that they've ever gotten. And this game ultimately now led manufacturers to start adding secret algorithms to their chips. So they know that we can see all the data flowing by, but what if everything is encrypted in a way that nobody has ever seen before? And that's what has been going on in the microchip domain, and this is exactly what we are breaking, just as we have been breaking the MIFARE chip. So we want to reverse engineer these very secret algorithms from the chips. So first we need to get to the chips, which usually is trivial. This, for instance, is an RFID ticket from the Moscow Metro, and the chip is in between these two antenna connectors, so it's a square millimeter about of a chip. To get to that chip, we throw it in acetone. The acetone dissolves the plastic around and either gives us the chip or gives us a small epoxy package where the chip is in. We throw that epoxy in nitric acid and we get the chip. So that step is fairly straightforward with household chemicals. Inside the chip, which is where we want to get to, we find structures like this. We find transistors built on top of a silicon substrate, and the different transistors are connected through these metal bridges. So each transistor is a little switch, and these metal bridges connect to different switches, and if you know anything about VLSI, you know that you can build an entire Intel processor using only these components. We want to take pictures now of these structures and reverse engineer the circuit that is described by them. And so we first want to take pictures of all the metal layers and ultimately of the transistors. And for this we need to cut through these different metal layers. So we basically have to cut through here to get to the transistors, for instance. This might look like they are free-flowing in this picture, but that's only because what is in between here is glass, silicon oxide. That's why you can nicely look through them. But often if you look from the different things block the view, so we really have to scrape them off, which is what Starbuck is doing with his bare hands and with some sandpaper, or preferably polishing paste. So he takes a tiny microchip and he starts polishing the microchip, sometimes using a polishing machine, and off micrometer by micrometer to get to these different layers. Sometimes the chip tilts a bit and he cuts through different layers at the same time, especially if the chip is very small. And he came up with this ingenious idea of just putting it with the plain backside, glue it to a block of plastic so you have something bigger to work with. And then again, he's polishing micrometer by micrometer. And next, we take pictures. Another way to get off these layers is by using hydrofluoric acid again. A little nasty to work with. If you get it on your skin, it will not actually hurt until it starts eating your bones, from what I understand. So, well, we have been working with it a bit. And it's a nice addition to the polishing. It has some different properties. So what the hydrofluoric will do is it will eat the glass in between the layers. And then these metal bridges that we have seen, they kind of break off the chip, especially if you polish them a little bit. So it's nice to combine this with polishing, but polishing has had better results for us, surprisingly. So however you get your layers off, you need to take pictures next, and we have been using a very standard microscope mostly. Something you'll find in a high school lab. A normal optical microscope, not too high magnification for the feature sizes we're looking at. FlyLogic, for instance, is using a confocal microscope, which has advantages because a confocal microscope shines light at different depths and then pictures only one depth at a time. So you get your picture nicely colored by depth, and it will look something like this, where you can tell that different lines are on different depths, so on different layers of the chip. And you can also look, for instance, up here. We have some glass left over in blue, but you can look through that glass. And a normal microscope would... yeah, so if you have access to a confocal microscope, it will get you beautiful pictures. If not, don't worry, we have been using normal microscopes all along. Yeah, so this is how you get pictures. Any questions, though? Is this clear? How you polish away microchips, how you take pictures? Easy, huh?
Do you polish a little and then look and then polish some more?
Right. Yeah.
Yes, we'll check.
Exactly. The question was how we know when to stop. We just keep polishing bit by bit, and we keep checking until it's deep enough. Well, next we need to stitch those various pictures that we take off the chip together. And we borrow a program, Huggin, from Panorama Photography. So we tell it this is a panorama, this is viewing, say, east, and this is viewing north. Please stitch them together. It will either automatically or manually assisted find reference points that it thinks correspond in each picture. We'll then stitch them together. So we do that for maybe up to 100 pictures to get one consistent view of a chip, one layer. And we do that for each layer, and that's all the input material we really need. Easy, huh? We'll get pictures out of this, of the transistors at the very bottom. On top of the transistors, they are grouped into logic cells. The logic cell could be an AND, an X, or any of that. And then those different logic cells are connected through these metal bridges on various layers. And then sometimes there's also a visual cover, so people can't reverse engineer it. These logic gates on the second layer from below. To understand them, you need a tiny little bit of VLSI. So this one, for instance, is an inverter. Consists of two transistors. There's one here and one up here. Each of them has 3 connectors. So these are the transistors. and the inputs to the transistors are connected to each other. The one will let current through when the input is high, the other one will let current through when the input is low, and